Hello students. So today this is our sixth lecture of redox reaction, and in this lecture we are going to conclude this chapter. So in the just previous lecture we discussed some of the multiple choice questions of one correct answer type and of more than one correct answer types. Besides these two types, there are several other types of questions asked in IIT JEE. So we are going to take today the remaining types of questions asked in IIT JEE. One very common question asked in IIT JEE, one very common type of question asked in IIT JEE in the recent year is questions based on comprehension, in which a comprehension, a passage is given based on the information in that passage and your knowledge of the subject. You answer the questions which follow the passage. Usually 3 questions, sometimes 2 questions are asked on one passage, and there is usually 2 or 3 passages every year asked in each subject in IIT JEE. So first we will be taking the question based on passage, which we call comprehension type of questions, and then we will be taking some other types of questions asked in IIT JEE. So I am going to write a passage, a comprehension, exactly the same type of comprehensions asked in IIT JEE. The comprehension is related to analysis of hydrogen peroxide. H2O2 is a good analytical reagent, used in redox titration as it is oxidized as well as reduced depending upon the nature of other reagents, as with strong oxidizing agent like KMnO4 or K2Cr2O7, H2O2 acts as a reducing agent with strong reducing agents like Ki, K2C2O4, etc. H2O2 acts as an oxidizing agent. So with strong oxidizing agent, it acts as a reducing agent, and with strong reducing agent like potassium iodide K2C2O4, it acts as an oxidizing agent. In one analysis, 20 ml portion of a sample of H2O2 in one analysis, 20 ml sample of H2O2 solution required 40 ml of acidic KMnO4 solution. Let us call it comprehension number 1, acidic KMnO4 solution. Also 20 ml of KMnO4 solution from the same stock required 9 ml 1 molar oxalic acid. Required 9 ml 1 molar H2C2O4 solution in an independent titration. Answer the followings. The first question is, what is molarity of original H2O2 solution? What is molarity of original H2O2 solution? And the options are 0.75 molar, 1.5 molar, 2 molar, and 3 molar. So let us work out this first, then we will be taking the another questions of based on this passage or comprehension. Here we are being informed that H2O2 is a good analytical reagent. It is used frequently. It is used frequently in redox titration, as it has the property of both oxidizing and reducing agent. When it reacts with a strong oxidizing agent like potassium permanganate, potassium dichromate, H2O2 is oxidized and therefore act as a reducing agent. Whereas when it reacts with strong reducing agent like Ki, potassium oxalate, it gets reduced and therefore acts as an oxidizing agent. Then a typical titration information is given. The 20 ml sample of H2O2 solution required 40 ml of acidic solution of permanganate solution. The information here is 20 ml H2O2 required 40 ml acidic acidic KMnO4 solution. In an independent titration, this 20 ml potassium permanganate require 9 ml 1 molar H2C2O4 solution. So from the second titration, we can determine the strength of potassium permanganate solution. How? How? 20 ml KMnO4 in acidic medium is equivalent to 9 ml 1 molar H2C2O4 solution. And we know that as a reducing agent, N factor of H2O2 is 2, oxalic acid is oxidized to CO2. So there is change of 2 unit in oxidation number for 1 molecule of oxalate ion. So N factor is 2. So 1 molar is 2 normal. So normality into volume correspond to 18 milli equivalent of H2O2 and therefore 18 milli equivalent of potassium permanganate also. So normality of KMnO4 solution will be 18 divided by 20. 18 divided by 20. Since 18 milliequivalent in 20 ml, so milliequivalent per ml, so it is 9 by 10, or we can say 0.9 normal. So now we know the normality of potassium permanganate, and as we know the normality of potassium permanganate, we can determine the normality of original H2O2. I think, yeah, something wrong is entered there. It is not 20 ml, I am very sorry, it is 12 ml. That's why I was thinking there is no correct option here. So it is not exactly 20, it is 12 ml. So normality of potassium permanganate will be 18 divided by 12. Let us correct it. 18 divided by 12. So 6 3 ja, 6 2 ja, so 1.5 normal. Now the normality of potassium permanganate is known. So in the original titration, in which 20 ml solution of H2O2 combining with 40 ml acidic permanganate solution, 20 ml H2O2 combining with 40 ml, now 1.5 normal KMnO4 solution. So if normality of H2O2 is N, implies 20 into N is equal to 40 into 1.5. So 22, it is 3 normal. So molarity of H2O2 will be normality divided by 2, since N factor of H2O2 is 2. So it would be 1.5 molar, and therefore the correct answer will be B, 1.5 molar. The next question is, what is volume strength of H2O2? Based on this passage is, what is volume strength of H2O2 solution, and the options are 8.4V, 8.4V, 16.8V, 22.4V, 33.6V. Now this question is related to volume strength of H2O2. As we know, we have defined several times in this chapter that volume strength of H2O2 is the volume of oxygen gas measured under a STP condition produced on complete decomposition of unit volume of H2O2. Based on this definition, we correlated the volume strength and normality of H2O2 in our previous lecture also. So we will not be deriving now, we will just be using the result we derived in the previous lecture, that for H2O2 volume strength is related to normality as normality is equal to volume strength divided by 5.6. Normality we have already derived in the previous case. So normality is 3, molarity is 1.5 and factor is 2. So normality is 3. So volume strength will be 5.6 multiplied by 3, and it is 16.8 V. So answer is B. Then the third part of this question is what are the oxidation states of H2O2 in the final product as it reacts with KClO3 and H2O3. What are the oxidation states? What are the oxidation states of product oxidation state of oxygen in product obtained on a reaction of H2O2 with KClO3 and AS2O3, and the options are -2, 0, 0, 0, 0 minus 2, 0 minus 1. This question is related to the reactions of H2O2 as an oxidizing agent and as a reducing agent. When KClO3 is oxidizing agent, it will oxidize H2O2 to oxygen, where the oxidation number is 0. H2O3 is a reducing agent. It will reduce H2O2 to H2O, where oxidation number of oxygen is -2. So the answer is 0 -2. C. There is one more question based on the same comprehension. If to the 30 ml of the above H2O2 solution, 20 ml of a 2 molar H2O2 is further added, volume strength of the resulting solution would be changed to. The question is, which is fourth question on this comprehension. If to 30 ml of the above solution of the solution of H2O2 20 ml of a 2 molar H2O2, 20 ml of a 2 molar H2O2 is added, what would be the volume strength of resulting H2O2 solution? And the options are 9.5 V, 12.75 V, 19 V, 22.6 V. This is very simple questions related to mixing of two solutions and determining molarity of the resulting solutions. So the original solution has molarity 1.5. So we'll apply the mixing formula here to find the molarity of the final solution first. First we will be determining molarity of the final solution by applying the formula M1V1 plus M2V2 is equal to M3V3. Original solution has molarity 1.5 and its volume taken is 30. So 1.5 into 30. Second solution has molarity 2, volume 20. So 220. Final volume will be 30 plus 20, 50. Let final molarity M3. So 0 will cancel off. So it is 3 into 1.5, 4.5, 4 here, 8.5 divided by 5. So M3 is 8.5 divided by 5. Is it correct? 3 into 1.5, 4.5, 4, 8.5 divided by 5, it's correct. 1.7 molar. So normality will be 2 times molarity. 1.7 into 2, so 3.4 normal. So volume strength with normality multiplied by 5.6. So 3.4 multiplied by 5.6. So if we multiply it, it is how much? 5.6, 3.4, so 19.04. So the correct answer is 19. It is 19. So now this way we complete the first comprehension. This is the type of questions being asked in current IIT JEE. So we must acclimate ourselves with this type of questions. We'll be taking two more comprehension of the same type. So let us move to the second comprehension of redox reaction, and this comprehension is very interesting one, in which we'll be using the concepts of a redox reaction as well as concepts of neutralization titration. So it is going to be a blend type of problems. So in this comprehension we'll have to apply the concepts of both redox reaction and a little bit of acid-base concept, acid-base titration as well. So this is our comprehension number 2. In this comprehension, it is being informed that oxalic acid H2C2O4 is a dibasic acid as well as a reducing agent. Whereas potassium hydrogen oxalate is amphoteric as well as a good reducing agent. In a typical analysis, 3 gram of a sample of H2C2O4 dot 2H2O, oxalic acid dihydrate, and KHC2O4 is dissolved in water and volume made up to 100 ml. This is the information given about a typical analysis of a mixture which contain both oxalic acid dihydrate and potassium hydrogen oxalate. Besides these two, there may be some impurity also. So now the questions follows this information. The first question is, a 10 ml portion of this solution, a 10 ml portion of this solution required 7.8 ml 0.05 molar H2SO4 solution. What is mass percentage of potassium hydrogen oxalate? And the options are 28%, 33%, 48%, and 60%. Let us answer this, then we'll be taking the next question based on this passage. A 10 ml portion of the stock solution requires 7.8 ml 0.05 molar H2SO4 solution. H2SO4 is a strong acid, and H2SO4 will just act as an acid during the titration, therefore it will neutralize only to base. And in the sample we have oxalic acid, which is an acid which will not react with H2SO4, but H2SO4 will react with potassium hydrogen oxalate, which is amphoteric, means which reacts as an acid as well as base. So how it reacts with sulfuric acid? Let us write the reaction first. Potassium hydrogen oxalate will react with H plus in the neutralization to give K plus and H2C2O4. So this is the reaction occurring in this titration only. And millimole of hydrogen ion will be equal to millimole of oxalate ion. So if we calculate the millimole of hydrogen ion, it would be volume of sulfuric acid 7.8 multiplied by molarity of sulfuric acid 0.05 multiplied by 2, because 1 mole of sulfuric acid gives 2 mole of hydrogen ion. So molarity will have to be multiplied by 2 in order to obtain the molarity of hydrogen ion. So we are interested here in hydrogen ion amount. So it is 0.1 multiplied by 10.8, so 0.78, which implies that 7.8 millimole, sorry, 0.78 millimole of potassium hydrogen oxalate is present in 10 ml of this solution. We are titrating 10 ml requiring this amount of sulfuric acid. So total millimole of potassium hydrogen oxalate is 7.8. Since 0.78 millimole of oxalate, potassium hydrogen oxalate is present in 10 ml, and we have produced originally 100 ml solution. So total millimole of potassium hydrogen oxalate in the original sample is 7.8. So total millimole of KHC2O4 is 7.8. So mass of KHC2O4 would be 7.8 divided by 1000 into its molar mass. Its molar mass is potassium is 39, hydrogen is 1, so 39, 1, 40, 40 plus 88, C2O4 is 88, 128. If we calculate it, comes out to be 128 multiplied by 7.8 divided by 1000, it is 0.9984. 0.9984. So you can say approximately 1 gram. If we convert it in percentage, so percentage mass would be 1 by 3 into 100, so around 33%. So the correct answer is B, 33%. Potassium hydrogen oxalate is 33%. The next question is, the next question of comprehension is, let us now remove the solution of first question here so that we can write the question number 2 based on this comprehension. So next question is, in a separate titration, 10 ml of the same stock solution, 10 ml of the same stock solution, 10 ml of the same stock solution required 14.15 ml 0.1 molar acidic KMnO4 solution. What is mass percentage of oxalic acid dihydrate, in original sample? And the options are 16%, 32%, 42%, and 64%. Now this is very interesting part of this comprehension. In a separate titration, 10 ml of the same stock solution required 14.15 milliliter 0.1 molar acidic permanganate solution. Now both oxalic acid and potassium hydrogen oxalate will react with potassium permanganate, since both of them are reducing agent and potassium permanganate is an oxidizing agent. So both oxalic acid dihydrate and potassium hydrogen oxalate will react with potassium permanganate. So milliequivalent of potassium permanganate now will be equal to sum of the milliequivalent of oxalic acid dihydrate and potassium hydrogen oxalate. So now we have 10 ml of same stock solution, 10 ml of the same stock solution, now require 7.12 ml, 0.1 molar acidic permanganate solution. What is the percentage of oxalic acid dihydrate in the original sample? So in the first question we have already determined that in 10 ml stock solution there is 0.78 millimole potassium hydrogen oxalate. Now if we assume, let 10 ml stock solution contain X millimole H2C2O4.2H2O. Now, N factor of both potassium hydrogen oxalate and oxalic acid as a reducing agent is 2. So, if we want to convert these millimoles into milliequivalent, we will have to multiply them by 2 each, and their sum will be equivalent to the milliequivalent of potassium permanganate. Therefore, 2 into 0.78 plus X will be equal to now 7.12 into 0.1 into 5, it is molarity, so multiplied by 5 normality, multiplied by volume, milliequivalent. If we solve it for X, multiply it and then multiply it and then divide it by 2, so 7.12 into 0.5, so 3.56 divided by 2, 1.78. So X will be 1.78 minus 0.78. It is 1. So now we have got millimole of oxalic acid dihydrate, X in 10 ml. So total millimole of H2C2O4.2H2O will be 10. Since this X 1 millimole in 10 ml. So total millimole will be 10 since we have prepared 100 ml of the solution. So total mass of H2C2O4.2H2O is 10 by 1000, 10 divided by 1000 into 126. So it is 1.26 gram. If we convert it into mass percentage, so mass percentage of H2C2O4 will be 1.26 divided by 3 into 100. We calculate, it comes out to be 42. So the answer for this second part is 42%. So in this titration, we used the information of the first question. In first question, we determined the millimole of potassium hydrogen oxalate by acid-base titration, and that we used in the second question in redox titration. Let us move to third question linked to this comprehension. Let us make some space by erasing these two questions also, so that we can write the next part of this comprehension. And the next question, which is third question based on link to same comprehension. This is question number 3. It is said that in a separate analysis, 20 ml of the above stock solution, this solution, 20 ml of the above stock solution reduces completely 9.5 ml of an acidic KMnO4 solution, acidic permanganate solution. What is the molarity? What is the molarity of KMnO4 solution? And the options are 0.1, 0.15 molar, 0.2 molar and 0.25 molar. Let us recall the previous information which we have derived in question number 1. 10 ml stock contain 0.78 millimole KHC2O4 and 1 millimole H2C2O4. This we have already derived in first two part of the question comprehension. Now 20 ml of the above stock solution. So we have information for 10 ml. So 20 ml stock solution will contain 2 into 0.78. So 1.56 millimole KHC2O4 and 2 millimole H2C2O4. Once again, this stock solution is being titrated with acidic permanganate. So some of the milliequivalent of oxalic acid and potassium hydrogen oxalate will be equal to milliequivalent of potassium permanganate. So milliequivalent of KMnO4 will be equal to milliequivalent of potassium hydrogen oxalate, which is 2 into 1.56 plus milliequivalent of oxalic acid, which will be 2 into 2. We are multiplying by n factor 2. So it is 7.12. It is 7.12. So normality will be milliequivalent divided by volume, 7.12 divided by volume, which is volume used is 9.5. So 7.12 divided by 9.5, 7.12 divided by 9.5, so it is 0.75. It is 0.75. So molarity will be normality divided by 5, so 0.75 divided by 5.15 molar. So the correct answer is B. Molarity of potassium permanganate used in this titration is 0.15. Next we move to fourth question based on the same comprehension. That will be the last question based on this comprehension. The question is, if 10 ml of the stock solution is titrated against 0.1 molar KOH solution, what volume of base would be required to reach the equivalence point, and the options are let us see what is this question. This time, a given volume of the same stock solution, which we prepared initially 100 ml, 10 ml of the stock solution is now being titrated against potassium hydroxide, which is a monoacidic base. Now, potassium hydroxide will neutralize oxalic acid to potassium oxalate and potassium hydrogen oxalate also to potassium oxalate. We can see the reaction also. So H2C2O4 will be requiring 2 mole of KOH to be converted into K2C2O4 plus 2H2O, and KHC2O4 will be requiring 1 mole of potassium hydroxide to be converted into K2C2O4 plus H2O. And now in 10 ml we already know the millimole of these two reagent. So in 10 ml we have 0.78 millimole of KHC2O4 and 1 millimole of this. 1 millimole of oxalic acid will require 2 millimole of potassium hydroxide, whereas 0.78 millimole of potassium hydrogen oxalate will require only 0.78 millimole of KOH 1:1. So 0.78 millimole. So total millimole of KOH required would be sum of this two, 2.78 millimole. And since molarity of KOH is 0.1, so volume of KOH required would be millimole divided by molarity. As molarity into volume gives millimole. So it is 2.78 divided by 0.1, so 27.8 milliliter. 27.8 milliliter. So the answer is C. So in this way, we are discussing the comprehension or linked type of questions exhaustively, and this is the real type of questions usually asked and expected to be asked in IIT. We'll be taking one more comprehension on redox reaction. That is very interesting to watch. That will definitely accentuate our understanding of redox reaction to a great extent. So let us see the next third comprehension on redox reaction and titration. So, comprehension number 3. This third comprehension This third comprehension is based on a redox reaction. H2O AXVY giving HaOY and X2V, and it is an unbalanced redox reaction. It is also given that in the redox reaction, oxidation number of X is -2, not undergoing change in oxidation number. Also, water is not involved. Water is not involved in redox process. So this is the information given for this particular question, comprehension. The first question is, the element undergoing reduction is, the options are A, B, Y, either B or Y. Which element is undergoing a reduction? Obviously, we'll have to find out the oxidation number of elements in the given redox reaction. Since it is said that neither water is involved in redox process nor X, and oxidation number of X is -2, so if X is -2, A must be +2 here. On the other side, we can see easily that hydrogen is +1, so A must be -1. A must be -1. So the element undergoing reduction is very obvious that it is A, since oxidation number of A is decreasing. Oxidation number of A is decreasing from +2 to -1. So A is undergoing a reduction, and therefore AX must be oxidizing agent itself. So the answer of the first question will be A. The next question on this comprehension is, the elements undergoing oxidation is R, and the options are A, B, Y, B, Y or both. B and Y, B or Y or both. Obviously A is not the answer since it is undergoing reduction. Now let us see the status of B and Y. On the right side, Y is fixed and it is plus 2. Y is plus 2 since O is minus 2. X is minus 2 and it is not undergoing change. So on the right side we have 2x minus 4, so B is plus 4. On left side we have B and Y here, and if we assume, say, Y is not undergoing any change, if we assume Y is not undergoing any change, then we can have oxidation number of Y plus 2 on both sides. And if we do so, if we write here By giving Y in plus 2 and B in plus 4, these two are fixed. The only thing is, on left side we'll have to verify what is happening with B and Y. So if we assume that Y is plus 2 on two sides, it is not undergoing any change. So B is minus 2 and it is undergoing oxidation since minus 2 to plus 4. It is possible. If we reverse this, if we say that B is not undergoing any change, so B is plus 1, plus 4 on two sides, so Y is minus 4, and minus 4 to plus 2, it is oxidation. It is also possible. So, in first instance, B is undergoing oxidation. In second instance, Y is undergoing oxidation. Now suppose we take Y as minus 1 arbitrarily. So B is plus 1. And in this process, Y minus 1 to plus 2 oxidation, B plus 1 to plus 4 oxidation, so both can be oxidized simultaneously. So only B can be oxidized, only Y can be oxidized, both can be oxidized, and therefore the answer will be D. The next is question number 3. Question number 3, based on the same comprehension. What are the possible oxidation number of B and Y? What are the possible oxidation number of B and Y in BY respectively? And the options are plus 1, minus 1, plus 2, minus 2, plus 3, minus 3, all of these is related to oxidation number. B and Y. Once again, let us write the information related to Vy. On right side, the oxidation number of Y is fixed, it is +2. Oxidation number of B is also fixed, it is +4. Is it possible to assign +1 -1? It is possible. If we assign +1 here, -1 here, it is undergoing oxidation. It is also undergoing oxidation. +1 to +4 oxidation, -1 to +2 oxidation. +2 -2, it is possible. +2 to +4 oxidation, -2 to +2 oxidation. +3 -3, it is possible. +3 -3, it is possible. Since B +3 to +4 oxidation, Y -3 to +2 oxidation, it is possible. So all these are possible oxidation number. So answer will be D. There is a last question based on this, that if the above redox reaction is balanced with simple whole number coefficients, sum of the coefficients of the reactants would be what? Options are 6, 7, 8 and 9. It is a very simple part of this comprehension. Let us balance it. Here we have 2 hydrogen, we will be balancing it just by trial. Here we have 2 hydrogens, so multiply here by 2. So 2A will come from 2AX. 1 oxygen, 1 O, final. So hydrogen, oxygen and A are balanced. 2X balanced. 2A, 2X, it's balanced. BY. So 2 plus 1 3 plus 1 4, 2 6, 1 7, 1 8. Some of the coefficients of reactants and products, combine them, otherwise answer will not come. Reactants and products. And products are so 8. So we have taken 3 comprehensions based on this redox reaction. There are many comprehensions, very challenging types of comprehensions are there in essential physical chemistry. So if you want to do further this type of comprehension, go and consult Essential Physical Chemistry of Arihant. So next and the last category we are going to take in this lesson is few questions of single integer answer types. Now we will be taking few questions of single integer answer type, in which informations of the questions are given in a manner that the answer of the question comes out to be a single digit integer. And we have to work out that question subjectively. So it is more or less subjective type of question. Subjectively we can answer this type of question only. So integer answer type questions we are going to take. The first question of this category is in the following reaction Ki plus KClO3 plus HCl giving ICl plus ICl plus KCl plus H2O if the reaction is balanced with smallest whole number coefficients, smallest whole number coefficients sum of stoichiometric coefficients of reducing agent and oxidizing agent would be what? This question is related to balancing of a redox reaction. So let us balance it, but by shortcut method. If we see iodine is undergoing change from -1 to +1 and chlorine from +5 to -1. So it is reduction of chlorine and oxidation of iodine. So half reaction is I minus giving I plus and ClO3 minus ClO3 minus giving Cl minus. If we see the change, here the change is of how many units? 2 units. -1 to +1. If we see the change here, it is +5 to -1, change of 6 units. So if we rationalize them, 1, 3, and as we know, we cross multiply the change in oxidation number to get the balanced redox reaction. So in the balanced redox reaction, the relation between these two will be 3 times Ki plus 1 times KClO3. Some HCl will also be there. Will give ICl. So 3I, so 3 ICl, KCl. We'll see how many KCl is required. and 3 oxygen, so 3 H2O also. And 3 H2O, for 3 H2O, 3 into 6 hydrogen will come from 6 HCl. So now it is, I think, 3 potassium, 1 potassium, 4 potassium, so 4 here. It is now completely balanced. So sum of the coefficients of reducing and oxidizing agent, 3, 1. So the answer is 4. 3 plus 1, 4. So this is the single integer answer of this particular question. Next question in this series, is this is question number 2. 15 ml K2C2O4 solution, potassium oxalate solution, require 25 ml slightly alkaline KMnO4, slightly alkaline KMnO4 solution for complete oxidation. For complete oxidation. If molarities of K2C2O4 and KMnO4 are rationalized to simple whole number ratio, sum of this ratio would be what? This is a very interesting question. 15 ml potassium oxalate require 25 ml of potassium permanganate. And in this question, potassium permanganate is being used in slightly alkaline medium. Therefore, the N factor of potassium permanganate is going to be 3. Potassium permanganate will change in oxidation number from +7 to +4 MnO2 is formed. Permanganate will be reduced to MnO2. So N factor is 3. Oxalate we all know. N factor is 2. If we take N1 with the normality of potassium oxalate and N2 with the normality of potassium permanganate, therefore, in this titration, milli-equivalent of K2C2O4 will be equal to milli-equivalent of KMnO4, and milli-equivalent is volume multiplied by normality. So 15 N1, 15 into its normality, will be equal to 25 into N2. 5 3 the 5 5 the. Now if we convert normality into molarity, we have to convert normality into molarity since the question requires molarity, and we know that normality divided by n factor, normality divided by n factor gives molarity. So if corresponding molarity be M1 and M2, then N1 will be equal to 2 times M1 and N2 will be equal to 3 times M2. So molarity multiplied by 3, normality of potassium permanganate, molarity multiplied by 2, normality of potassium oxalate. So if we replace normality in terms of molarity, we find 3 into 2m1 will be equal to 5 into 3m2. So m1 is to m2 is 5 is to 2. So sum of the ratio is 5 plus 2, it is 7. So answer of this question is 7. Move to the next questions of similar category. Question number 3. This question is related to reaction of potassium cyanide with potassium dichromate. Question is, in the reaction KCN plus K2Cr2O7 plus H2SO4 giving K2SO4 plus CO2 plus NO plus Cr2SO4 whole 3. If 6 ml of potassium cyanide is titrated against acidic dichromate solution of same molarity, if 6 ml of potassium cyanide is titrated against K2Cr2O7 solution of molarity same as that of KCN, what volume of oxidizing agent would be required? In this question, the similar molarities of oxidizing and reducing agents will have to be used. So let us find out their N factor first. If we write this reaction where change is occurring, cyanide Cr2O7 2 minus giving CO2 plus NO plus Cr plus 3 to use. So N factor for dichromate is known to us, that we are using frequently. What about cyanide? In cyanide, nitrogen is -3. So carbon must be +2. On the right side, carbon is +4 and nitrogen is +2. So for one cyanide, change in oxidation number is 2 for carbon plus -3 to +2, -3 to +2, 5 for nitrogen. So it is 2 plus 5, 7. So N factor for cyanide is 7. Let M be molarity of both solution. Now equate their milliequivalent. So 6 ml potassium cyanide, 6 into molarity into N factor 7. For cyanide we have determined N factor 7 is equal to V if volume of dichromate required into molarity into 6. N factor is 6. Molarity will cancel out, 6 will cancel out. So V is 7 ml. So for titration of 6 milliliter of potassium cyanide, 7 milliliter of potassium dichromate will be required. Let us take one more question to close this chapter. We will be closing this chapter with this last questions, practicing on single integer answer type question. This is related to determination of volume strength of H2O2. The question is, what is volume strength of a H2O2 solution whose normality is 1 divided by 1.12 normal. 1.12 normal. Volume strength of H2O2. Once again, it's a very important concept of hydrogen peroxide. Volume strength of H2O2. H2O2 decomposes to give H2O and half O2 gas. So volume strength of H2O2 is defined as the volume of oxygen gas produced at STP on complete decomposition of unit volume of H2O2. So if we take X as the volume strength, means 1 liter H2O2 will produce X liter oxygen at STP, and X liter of oxygen implies X upon 22.4 mole oxygen, and for oxygen n factor is 4, so X upon 22.4 into 4, so X upon 5.6 equivalent. And if this is the equivalent of oxygen, the same will be the equivalent of H2O2 in 1 liter, and that will be the normality that we have done previously also. So normality is nothing but volume strength divided by 5.6. So volume strength will be normality multiplied by 5.6. So here we have normality 1 upon 1.12 into 5.6. So it is 5, and this is the answer of our question. So by this way we have completed the redox reaction in 7 lectures, and all the lectures were of more than 2 hour duration. It's a very challenging chapter, but very rewarding also. One questions always comes in JEE Mains, JEE Advanced, and if it is done properly, then we can go with more than 100% surety that the question of redox reaction will be answered appropriately and accurately.